So a map projection is a mathematical conversion of points on the Earth's curved surface to points on a flat plane. And once again, in this example, we can see there's a light bulb in the middle of a clear globe. And as we shine the light through, all those lines of longitude and latitude on the surface of this globe would be projected onto this piece of paper here, which is curved into half of a cylinder. And once that cylinder is flattened, these are the lines of latitude and longitude that would result. So the Earth's shape is defined by the geographic coordinate system, and your choice of datum is going to slightly affect where different points are projected onto a flat plane. Here's kind of a famous example here between NAD 27 and NAD 83. If you have two different data sets and one was projected into NAD 27 and one was projected into NAD 83, they could be offset by amounts like this, where things are just a little bit shifted and nothing quite looks right and nothing quite lines up. So if you are having this issue where your data doesn't look the way it should, we can see this curved line up here, should be up in this area here, then one thing to check is that both of the datums for those data are correct. So how can we project around Earth onto a flat piece of paper? Well, we have to have either a flat piece of paper, as is shown in this example C here, or we have to have some sort of shape like a cylinder or a cone that we can take and we can flatten it out without causing any distortion except where we cut it, and then everything else flattens out perfectly. So the lines of longitude and latitude are going to have these kind of shapes. If we start with a cylinder and we put it around the sphere and then we project from the sphere onto the cylinder, we're typically going to have parallel lines of latitude and parallel lines of longitude. However, if we start with a cone, these lines of longitude are all going to point up towards the top of the cone, as we see here, and the lines of latitude are actually now going to be curved lines. And with this case here, which is sometimes called the azimuthal map projection, where we're projecting onto a flat surface, that's just going to result in some sort of curved patterns of latitude lines and potentially straight or curved longitude lines as well. If we did this on the North Pole, if we had our plane up here instead of on the side on the equator, then we would almost see like a bullseye where the North Pole would be a point, and then we would have circles of latitude, and then we would have radial circles of longitude moving away from the North Pole. So we can have cylindrical, conic, or azimuthal map projections, and each one of these, as it says here, has a different property. When we're doing a map projection, we're going to have to set some parameters. And so we'll just talk about what these parameters are. For a conic map projection, we can have one line where the cone is actually touching the sphere. And that's shown by this line here. And that would be a line of no distortion, because you can think if the sphere here had ink on it, that would be the one point where we'd actually get an ink print onto this piece of paper that's shaped like a cone from the sphere itself. But we can actually get two lines of this no distortion if we cut our cone through the sphere here, it's underneath the sphere here, and then it comes back out above the sphere here. So this is called a tangent case because the cone is only touching at one line here, and this is called a secant case because we have two lines. As we'll see here, these lines where there are no distortion on this cone are called standard parallels. We'll talk about central meridians in a minute, the latitude of origin, but two other things we might notice here is this false easting and false northing. In every map projection, we would have a point that is 0, 0, and from there, sometimes we just offset the data to the north or to the east. And this is just a convention that we use in order to better fit things onto a map. But the distance we set it off to the east would be called the false easting, and the distance we set it off to the north, this blue line here, would be the false northing. So here are those standard parallels again here. Once again, no distortion along these lines of standard parallel, and there are distortions in other places. In this case here, we have two lines of standard parallel because it's a secant case. And if we looked at what that looked like on a map, we might see something that looks like this. This is actually this is not a conic map projection, but a cylindrical one, but the same sort of idea. We're going to have two lines cutting through the map, and along these lines there's going to be no distortion. So the tangent case has one standard parallel, the secant case has two standard parallels. We tend to use the secant case just because we have more of our map area that doesn't have distortion if we use the secant case. So that's what the standard parallels are. And then the central meridian, if we think about a cylindrical map projection, we can orient the cylinder any way we want to. If this is the North Pole and this is the South Pole, we can put it so we have one line where, once again, the cylinder is touching the sphere along this line here, and in this case, it would be a line of longitude. Or we could take the cylinder and rotate it 90 degrees, and now, if this is once again the North Pole and the South Pole, this one line of no distortion would run right along the equator. So we can have these different things here. This is going to help us define where the origin is. This is going to be a line of 0 latitude, so it's going to have a value of 0, and values are going to increase as we go up and down in this direction and down in this direction. And because of that, we can also talk about the extent, or the x and y values that represent all of the data on our map. So these, once again, are the central meridians. So with any of these sorts of maps, we always have distortion. It's just impossible to take a spherical surface like the surface of the Earth and try to make it flat without either stretching or pulling or cutting or squeezing different areas in different parts of the map. So with any sort of flat map, we're going to either have distortion of direction on the map. A direction that looks like a straight line on this map might not actually be the shortest distance, or the straight line on the surface of the Earth. We can have distortion in the shape of things on the map. We can have distortion in the areas of things on the map. And we can have distortion in the distance of things on the map. Usually a map projection at best can get one of these right. So you can have a map with no distortion in shape, but there might still be distortion in distance and area and direction. So cylindrical projections, they usually preserve direction and shape. So on this cylindrical projection, even though Greenland is much larger than it really is here, the shape of Greenland, all the inlets and outlets and that sort of thing, is pretty much what we would see on a globe. So there's no distortion in shape there. And of course, one of the nice things about this map is you can draw a straight line on this map, and it's going to be a line of constant bearing. You could just take a bearing with your compass and sail off in that direction, and you would be going in the right direction. With conic map projections, we can arrange these so they have no distortion in area. So what we're seeing here would really represent the area of the United States. And we can also make conic map projections that have no distortion in distance. For azimuthal map projections, usually these, sometimes they have no distortion in distance, and they can also sometimes have no distortion in area. So different sorts of map projections, their whole job is to sort of minimize these distortions as we make these flat maps from the curved Earth.